In this video, we're going to look at the concept of momentum. We're going to understand what momentum is. We're going to use the equation for momentum. And we're also going to understand and use something called conservation of momentum to solve problems. Pause the video and do these questions. Press play once you've done them. You should have now done these two questions. Please mark them as I go through them. So for question one, remember that velocity is what type of quantity? Say your answer to the video now. Velocity is a vector quantity, which means it includes direction. So if it's originally moving at 5 meters per second north, let's say that that's 5 with a positive before it, so plus 5 meters per second. And then later it's moving at 3 meters per second in the opposite direction. That means its final velocity was -3 and its initial velocity was 5. So the change in velocity is -8 or 8 meters per second. So what I've done there is I've done the final velocity minus the initial velocity. So the final velocity was -3, the initial velocity was 5. So the difference between them is -8. What change do you need to undergo to go from +5 to -3? You need to -8. And for question two, the answer is yes, it is accelerating because velocity is a vector quantity. So yes, because velocity and acceleration are both vector quantities. So a change of direction is a change of velocity and therefore acceleration. Please pause the video to mark your work. Press play once you've marked it. So you should have now marked your work. So these are a couple of concepts that are important to understand the rest of this lesson on momentum. So we're going to start now with the definition of momentum and its equation. So momentum is the overall oomph of something moving. Now, what do I mean by that? Well, a good way of explaining it is how hard it is to stop something which is moving. Or let's say you were going to apply a certain force. So let's say you were going to press the brakes to stop something. How long would you need to press those brakes for to stop it? So for example, a really heavy lorry. So let's say here's a really heavy lorry. Let's say it's 3,000 kilograms. And let's say it's moving at a speed of 3 meters per second. And then let's say we have a much lighter car. Let's say that's only 300 kilograms. And it's also moving at 3 meters per second. Which of those is going to be harder to stop? Say your answer to the video now. Hopefully you've said the lorry. Why is the lorry harder to stop? Say your answer to the video now. You should have said because it has a bigger mass. So mass clearly has something to do with this. Now there's something else which has to do with it as well. So let's say we had another lorry, which was also 3,000 kilograms. But this lorry was moving at 7 meters per second. Which of these two lorries, A and B, would be harder to stop? Say your answer to the video now. You should have said the one moving at 7 meters per second. So clearly speed has something to do with this as well. So both the mass of something and the velocity that the thing is going make it more difficult to stop. The heavier it is, the more difficult to stop. The faster it's going, the more difficult to stop. And momentum is a mixture of those two things. So momentum is mass times velocity. So we use the letter P for momentum, M for mass, and V for velocity. Let's check that you know your units. What are the units for mass in physics? Say your answer to the video now. Should have said kilograms. What are the units for velocity? Should have said meters per second. And that means mass times velocity is kilograms times meters per second. So the units for momentum are kilogram meters per second. Notice that part of the equation here is velocity. Momentum depends on velocity. So what type of quantity do you think momentum is? Say your answer to the video now. Momentum is a vector quantity. Momentum is a vector quantity. And that's because it depends on velocity. So velocity is a vector quantity, therefore momentum is as well. So that means direction matters. So let's have a look at some examples to understand this in more detail. So firstly, using the equation which we just learned, momentum is mass times velocity. Pause the video, have a go at this question, press play once you're ready. You should have now done this question, or at least had a go at it. I'm now going to go through it step by step so you can see if you did it the right way. Please mark your work as I go through it. So we're told that the momentum is 89.7, and we're told the mass is 245 grams. So I need to turn that into kilograms. So 0.245 grams is going to be, sorry, I've already converted it. I jumped ahead. 245 grams is 0.245 kilograms. I've divided 245 by 1,000 there. So 89.7 is 0.245 times the velocity, which means the velocity must be 89.7 minus 0.245. You're always allowed to use a calculator when you're doing physics. So 89.7 divided by 0.245, and I need to give my answer to 3 significant figures, so 366 meters per second, which is just a bit faster than the speed of sound. Not sure what this object is. It's just a made-up object. The speed isn't a very realistic speed for most 245 gram objects, but we just follow the equation and follow the steps. Next example, pause the video, have a go at it, press play once you've had a go. Okay, so let's have a look at this. The point at the beginning is that they're both going in the same direction. And remember that momentum is a vector quantity. So at the beginning, we've got the car, and the car's momentum is going to be mass times velocity, which is 400 times 10, which is 4,000. And the units, what are the units for momentum? Say your answer to the video. Hopefully you've said kilogram meters per second. And then we have the van, and we use the same equation. The mass is 800. It's moving in the same direction, so the velocity is also a positive number, 6. Then we have 800 times 6, which is 4,800 kilogram meters per second. So that means the total, you just have to add the two together. So we get 8,800 kilogram meters per second. But then question B starts to think about the fact that momentum is a vector quantity. So if they're moving in opposite directions, that means one of them is going one way. So let's say this is the car going to the right with a momentum of 4,000, and the van is going to the left with a momentum of minus 4,800. So this time their total momentum is 4,000 plus minus 4,800. And that makes minus 800 kilogram meters per second. If you've written just 800 kilogram meters per second, that's also fine. It just depends which direction you've taken as your positive direction. I could have equally put this minus in front of the 4,000 instead. And if I'd done that, I would have got an answer of positive 800. So direction matters. Momentum is a vector quantity. Finding the change of momentum when something stops. So at the beginning, when it was moving, it had a momentum of 4,000 kilogram meters per second. When it stops, what will its momentum be now? So this was at the start. What will its momentum be at the end when it stopped? So your answer to the video now. Well, if momentum is mass times velocity, its mass is still 400, but it's not moving anymore, so its velocity is 0. So its finishing momentum is 0 kilogram meters per second. So that means its change in momentum is minus 4,000. You could also say 4,000, as long as you've got that number 4,000 in there. That's its change in momentum. And finally, we need to work out a change in momentum of the van. So we need to start by working out the starting momentum. So I'm actually going to call that PI, I for initial. So let's work out the initial momentum of this van. So it was 800 times 6, which is 4,800 kilogram meters per second. Then it changes direction and finishes at 8.4 meters per second in the opposite direction. So its final momentum is going to be the mass 800 times 8.4 in the opposite direction times minus 8.4. You're always allowed to use a calculator. So I'm going to do that on my calculator now. And I get minus 6,720. The difference between those two numbers, so I'm going to do minus 6,720 minus 4,800, and that gives me a change. Let's actually use the delta symbol. The change in momentum of minus 11,520 kilogram meters per second. Mark those answers, make sure you understand them, and then let's move on. So pause the video, have a go at this example, press play once you've had a go. You should have now had a go at this example here, and the answer is no, they do not. And that's because momentum is a vector quantity. And that means that a change in momentum a change in direction means a change in momentum. So here we have two objects moving in different directions. It doesn't matter that they have the same mass and velocity. Well, it doesn't matter that they have the same mass and speed. They do not have the same velocity because they're moving in different directions. So they therefore have different momenta. They will have the same magnitude of momentum. So the size of their momentum, the number of their momentum will be the same, but the direction of their momenta will be different. So now we're going to look at a concept called conservation of momentum. So the idea of conservation of momentum is during an event, and what I mean by an event is a collision between two objects, or an explosion, which is when one object splits into two parts which go flying off in different directions. So during an event, collision or an explosion, the total momentum before the event equals the total momentum after the event, as long as there's no external forces acting. And that's a really important definition. So please pause the video to write it down. Press play once you've written it down. You should have now written down this definition of conservation of momentum, but to really understand it, we need to actually do it. We need to actually do some stuff. So we're now going to look at some conceptual examples. So imagine I have a toy car, which is fan powered. So there's a fan at the back, which makes the toy car move forwards. So there's this fan at the back, which spins around and makes the car move forwards. So this is to do with Newton's third law, which you will have already studied. So the fan pushes back on the air. What's the Newtonian pair to that? Say your answer to the video now. You should have said that the air pushes forwards on the fan. And that makes the car go forwards. But this can also be explained in terms of this idea of conservation of momentum. Before we switch on the fan, what is the momentum of the system? What is the momentum of the car and fan together? Say your answer to the video now. Well, before anything happens, the car and the fan are not moving. So the velocity of them is zero, so their momentum is zero. So that means because of conservation of momentum, what does the total momentum have to be after we switch the system on, after the fan is spinning? So the momentum still needs to be zero. So how is that achieved? Well, the momentum which the car gains is equal and opposite to the momentum which the air gains. So let's say that the car gains a momentum of 0.2 kilogram meters per second. So that's the car's momentum after we switch on the fan. Well, the momentum of the air will be minus 0.2 kilogram meters per second. And what that means is when you add together this and this, what is the sum of minus 0.2 and 0.2? So your answer to the video, you should have said 0 kilogram meters per second. So the momentum is still 0. Let's look at a very similar example to that. So imagine somebody has a skateboard and they jump off the skateboard. So here is somebody who is jumping off the skateboard. So as they jump off, the skateboard recoils backwards. And we're going to explain why the skateboard recoils backwards. So when the person jumps off, they push back on the skateboard. So again, we have Newton's third law. Pause the video and write down the Newtonian pair when the person jumps off the skateboard. Press play once you've done that. You should have now written down the Newtonian pair when the person jumps off the skateboard. So the idea is that the person pushes back on the skateboard, and therefore the skateboard pushes forwards on the person. So both of those happen at the same time. That's a Newtonian pair. And we can explain that in terms of momentum as well. So before the person jumps off, what is the total momentum of the skateboard and person together? Say your answer to the video. Well, the total momentum will be 0 because they're not moving. And when the person jumps off, the total momentum still needs to be 0. And that's achieved in the same way that the person might have a momentum in one direction, let's say of 20 kilogram meters per second. The skateboard will have exactly the same magnitude of momentum, but in the opposite direction. So that minus 20 plus 20 makes 0 as well. Let's look at some more conceptual examples. So pause the video, read this example, press play once you've read it. Okay, you should have now read this example. Please now try the example, pause the video while you do that, and press play once you've done it. So you should have now written down your thoughts to this. So from writing down your thoughts, we're going to get to the point where you understand the maths. So we've got two identical trolleys, one stationary and one moving. So I'm actually going to draw the situation. So I've said that they're identical, which means they have the same mass. So I'm going to label them both with an M for mass. One of them isn't moving, so its velocity is 0, and the other one is moving. So let's draw an arrow to show that it's moving. And they collide and stick together. What happens to the speed of each trolley? Well, what's going to happen is that the two are going to stick together. We've now got a total mass of what? Say your answer to the video. The total mass is now 2m. Now, since we still need the same amount of momentum, this one, let's call it trolley 1, is going to have to slow down. And this one, trolley 2, is going to have to speed up. And what actually happens is we get an overall speed of exactly half the original speed of trolley 1. And we can actually just quickly check that that works. So what was the total momentum at the start? Well, the momentum of 1 was m times v, and the momentum of 2 was 0, because it wasn't moving. And the momentum at the end, well, that you got the two together. So the mass is 2m. The velocity is now v over 2. That still equals mv. So the total momentum at the start was mv, and the total momentum at the end is still mv. So when two identical trolleys, one stationary, one moving, collide and stick together, the speed of the overall trolley combination at the end is half the speed of the trolley that was moving originally. Pause the video, write down your thoughts to this one, press play once you've done that. You should have now written your thoughts to this one. So we still have two identical trolleys, both with a mass m. This time one is moving faster than the other. So let's make this one a big V, and this one a little v. And they collide and stick together. So after the collision, we've now got this combination of 2m. Well, this time what we actually get is the average speed of the two. This will actually be the average speed of the two. So what happens is, if we call this one trolley 1, this one slows down, and this one trolley 2 speeds up, so that at the end, the overall momentum is still the same as at the beginning. We'll do some numbers soon. Pause the video, write down your thoughts to this one, press play once you've done that. You should have now written down your thoughts to this one. So let's draw the diagram again. So we've got a trolley moving to the right with velocity v, and a trolley moving to the left with velocity v. So in this case, we can actually see that the total momentum at the start, well, this one, trolley 1, has a momentum of what? Say your answer to the video. You should have said m times v. And what's the momentum of this one, trolley 2? Well, you shouldn't have said m times v, you should have said minus mv. Why? Say your answer to the video. Well, it's moving in the opposite direction. So the total momentum before the collision is mv minus mv, which is 0. So the total momentum after the collision needs to be what? Say your answer to the video. The total momentum after the collision needs to also be 0. So what actually happens is they just completely stop. So they'll crash into each other and they'll stop. Let's look at another example. Pause the video, write down your thoughts to this one, press play once you've done that. You should have now written down your thoughts on this one. So we've got one heavier than the other. So let's make that one a big M and this one a little m, moving towards each other at the same speed. But this time, the momentum of this one is going to be capital MV, and the momentum of this one's just going to be little mv. So when they stick together afterwards, you're going to have one big trolley combination with a mass of big M plus little m, but it's going to carry on moving in this direction, but at a lower velocity than the velocity of, if we call that one 1 and that one 2, with a lower velocity than 1 had at the beginning. So trolley 1 dominates because it has a bigger mass. So the overall motion will carry on in the direction that trolley 1 was originally moving in because it's heavier, but it will slow down so that momentum is conserved. Now, looking at these conceptual examples, it isn't always exactly clear what exactly happens numerically. So we're going to do some numerical examples now. So I'm going to do this example fully by myself. Please pause the video, read the question, press play once you've read it. You should have now read this question. So I'm going to do this question fully by myself. So I'm going to start by drawing a diagram. So I've got 2 trolleys and they're identical. So they both have a mass of 26 kilograms. But this one over here is stationary, so V is 0. This one over here is moving at 2 meters per second. I'm going to call this before, because this is before they've collided. Now, after they collide, they're stuck together. So the new mass is now 26 plus 26, which is 52. And we need to work out the final velocity of that combination of the 2 trolleys. So we do it by using conservation of momentum. Now, in an exam, you should write down a statement of conservation of momentum. So you should write down the total momentum before the collision equals the total momentum after the collision, as long as no external forces act. So you would always write that down in an exam. I'm just going to do the maths part of it now. So we work out the total momentum at the start. So the momentum of, let's call this one trolley 1, and this one trolley 2. So the momentum of trolley 1 is mass times velocity, 26 times 2, 52. The momentum of trolley 2, it's not moving, so it's just 0. So the total momentum at the start is 52 kilogram meters per second. That means the total momentum at the end has to be the same because momentum is conserved. So now I know that the total momentum at the end is 52, and I know that the mass at the end is 52 kilograms. So I just substitute that into this formula, and I can find what V is. It will be 52 over 52, which is 1 meter per second. I'm just going to make sure that makes sense conceptually. So trolley 1 was moving at 2 meters per second, trolley 2 wasn't moving. It makes sense that when they collide together and stick together, the motion should be slower than 2 meters per second. If it's sped up, that means momentum would have been gained from nowhere, which is impossible. So it makes sense. In fact, if you have a look, this is double the mass of this, and therefore it makes sense that the velocity should have halved so that momentum is conserved. So pause the video, have a read of how I did this question again. If you found that challenging, you could even go back in the video, try the example yourself, because we're now going to do another one together. So you should have now gone back in the video if you found that example difficult, and you should now be ready to move on. So we're going to do this example together. So pause the video, have a go at it, press play once you've had a go. You should have had a go at this question now. So as I go through it, please make notes and corrections. So we start by drawing a diagram. If you've not drawn a diagram, pause the video and draw a diagram. It's a really important part of the process. So we've got a 3,000 kilogram truck moving at 16 meters per second, and it's going to crash into the back of a 1,000 kilogram car moving in the same direction at 4 meters per second. That's my before picture. Then I'm going to draw an after picture. and the two vehicles move together after the impact. So what's the total mass of the two vehicles once they're stuck together? Say your answer to the video. The total mass is 4,000, and we're trying to find the new velocity. What letter should I use for the new velocity? Say your answer to the video. I'll use the letter V. So let's work out the total momentum before. So what's the momentum of this one before? Say your answer to the video now. Well, you can always use a calculator if you find this kind of thing difficult, but it's 48,000 kilogram meters per second. What's the momentum of this one before? You should have said 4,000. So what was the total momentum before the collision? Say your answer to the video. You should have said 52,000. So what's the total momentum after the collision? Say your answer to the video. Also 52,000. Why? You should have said because of conservation of momentum. So now we use the equation, P equals mv, 52,000 equals 4,000 times V. So V is 52,000 over 4,000. You can always use a calculator, and that will equal 13 meters per second. And that kind of makes sense because it's somewhere between 16 and 4, and it's actually closer to 16. Why is it closer to 16? Think about it, pause the video, press play once you've got an answer. So you should have now thought, why is it closer to 16? Well, it's closer to 16 because this one was heavier than this one. So this speed is going to dominate over this one. There's a second part to the question, which is find the total kinetic energy before and after the collision. So let's do the total kinetic energy before. What's the equation for kinetic energy? Say your answer to the video. So you should have said half mv squared. So I'm going to do half mv squared for both. So we've got a half times 3,000 times 16 squared. And we need to add to that a half times 1,000 times 4 squared. Now you're always allowed to use a calculator when we do physics. So that's what I'm going to do to make sure I don't make a mistake. So the answer is 392,000 joules. Now I'm going to work out the total kinetic energy after. If you got the wrong answer for your total kinetic energy before, pause the video now and work out the total kinetic energy after the collision. Press play once you're ready. You should have now tried again to work out the total kinetic energy after the collision. So it's going to be half mv squared. So that'll be half times the new mass, which is 4,000, times the new speed, which is 13 squared. We use a calculator, so we got half times 4,000 times 13 squared, which is 338,000 joules. So what's happened to that missing energy? Well, during the collision, there'll have been a transfer of energy from the kinetic energy store to which store? Say your answer to the video now. Energy will have been transferred to the thermal energy store of the bodies of the car and of the surrounding air. Generally, when energy seems to disappear from a situation, it's transferred to the thermal energy store of the surroundings. We're going to do this example together now. So pause the video, have a go at it, press play once you've had a go. You should have now had a go at this question. I'm going to go through it. Please mark and correct your work as I go through it. So we've got a 10 kilogram object traveling at 6 meters per second, and it collides with a stationary object of mass 12 kilograms. So that's not moving at all. The objects do not stick together, so that's before. So then afterwards, they're not stuck together. So this is actually a bit different. So the 12 kilogram object is now moving at 4.5 meters per second. And we need to work out the final speed of the 10 kilogram object, but they're not stuck together. But let's follow the same process. So we start with conservation of momentum. So we work out the total momentum before. So the momentum of this one, 10 times 6, 60 kilogram meters per second. This one isn't moving, so it has a momentum of 0. So the total momentum before is 60 plus 0, which is 60. Therefore, what's the total momentum afterwards? Say your answer to the video. You should have said it's still 60 because of conservation of momentum. So let's work out the momentum of this one. So the momentum of this one is 12 times 4.5, mass times velocity. So 12 times 4.5 is 54. So what does that mean the momentum of this one must be? Say your answer to the video. It must be 6, because if the total momentum after the collision is 60, and the momentum of the 12 kilogram mass is 54, the other one must be 6, so that they add together to make 60. And now we know its momentum, we can use the equation 6 equals 10 times V. 6/10 equals v. So v equals 0.6 meters per second. That's collisions. There's another type of event which we need to understand mathematically, and that's explosions. So just to explain what an explosion is, pause the video, read the question, and then I'll talk about what an explosion is. You should have now read this question. So an explosion is when you've got two objects that weren't moving, and then something happens and they now move apart from each other. So a standard example is a gun and a bullet, or in this case, a gun and a shell. And the idea is that always before an explosion, there is no motion at all. You have the gun, and the shell is still in the gun, and they're not moving. So the momentum before is 0. Afterwards, the shell is now moving off at a very high velocity, and it has a mass of 20 kilograms. What that means is, for the momentum to still be 0, the gun must have what we call a recoil velocity in the opposite direction, just like the examples of the skateboard before and the fan-powered toy car, where one thing moved one way, something else had to move the other way, so that the total momentum was still 0. So once we realize that, the situation becomes quite simple, because if the total momentum has to be 0, we just work out what the momentum of the thing moving one way is. So it'll be 20 times 120, which will be 2,400. That means the momentum of the thing going the other way must be the same, just in the opposite direction. So minus 2,400. And that means we can easily work out the velocity by doing momentum over mass, minus 2,400 over 2,000. And that leaves us with minus 1.2 meters per second. And what we can see is that because the gun was 100 times bigger, or 100 times more massive, it had a 100 times higher mass than the shell, that means its recoil velocity was 100 times smaller than the velocity of the shell. So the one with the bigger mass has the smaller velocity, and the one with the smaller mass has the bigger velocity, so that their momenta, or at least the magnitude of their momenta, are the same, even though the directions are opposite. So just to summarize what we do when there's an explosion, the total momentum before the explosion is 0, so the total momentum after the explosion must also be 0. So we work out the momentum of one of the things, the momentum of the other must be the same magnitude, just in the opposite direction, so that they still add together to make 0. Pause the video, try this example yourself, press play once you've done it. You should have now done this example yourself, so I'm going to go through it. So we've got an 80 kilogram person, and we've got a 50 kilogram person, and they push each other apart. And the 80 kilogram person starts to move at 0.4 meters per second. We need to work out what speed this person moves. So at the beginning, the total momentum was what? Say your answer to the video. At the beginning, the total momentum was 0. So what's the total momentum at the end after they push each other apart? Say your answer to the video. The total momentum still needs to be 0. So we work out the momentum of this person, 80 times 0.4, which will be 32 meters, well, kilogram meters per second. That means the momentum of this person must have the same magnitude. And then we can just use the formula, 32 equals 50 V, 32 over 50 equals V. So V will be 0.64 meters per second. And again, notice the heavier mass, smaller velocity, the smaller mass, bigger velocity. So that when you multiply mass and velocity, you get the same answer for each. They should each have a momentum of the same magnitude, just opposite directions. You're going to do some independent practice now. Pause the video to do these questions, press play once you've done them. You should have now done these questions. Pause the video to mark and correct, press play once you've done them. You should have now marked and corrected those questions. Pause the video to do these questions, press play once you've done them. You should have now done these questions. Pause the video to mark and correct those questions, press play once you've done that. You should have now marked and corrected those questions. Press pause to do these questions, press play once you've done them. You should have now done these questions. Pause the video to mark and correct those questions, press play once you've done that. You should have now marked and corrected those questions. Mark this question now. Pause the video while you do that. Press play once you're ready. You should have now marked and corrected this question. Pause the video to do these questions. Press play once you've done them. You should have now done these questions. Pause the video to mark and correct those questions. Press play once you've done that. You should have now marked and corrected those questions. Pause the video to do these last two questions. Press play once you've done them. You should have now done these two questions. Pause the video to mark and correct those questions. Press play once you've done that. You should have now marked and corrected those questions. So overall, we've learned what momentum is, but the main idea is this idea of conservation of momentum. And that means before an event, what's an event? Say your answer to the video. You should have said that an event is a collision or an explosion. Total momentum before the event is equal to the total momentum after the event, as long as no external forces act. I hope this video was useful. Please like and subscribe for more videos on GCSE physics.